Okay, so here's the answer key to some of the additional thermochem practice problems we were looking at before the test. First one is just sort of a conceptual thing where you have to remember that the specific heat is equal to the amount of energy required to increase 1 gram of a substance by 1 degree Celsius. So therefore, the greater the specific heat, the greater energy it takes to increase that substance, or the heat of that substance, the temperature. So assuming you're applying the same amount of energy to two different substances, it will take longer for the substance with the higher specific heat to go up. Therefore, the answer is it will take longer to increase the temperature of substance A because it has a greater specific heat. Okay, so we're looking at now taking two objects at two different temperatures, two different masses, two different specific heats, and putting them together until they reach an equilibrium. So one is going to warm up, one is going to cool down as they exchange energy. And we're going to use the formula that the change in energy is equal to the mass of the substance times its specific heat times the change in temperature. And we're going to assume, since no heat is lost, that the change in energy of the gold metal is equal to the change in energy of the iron metal. So whatever heat is gained by the gold is being lost by the iron, which means that we can take the equation for the change in energy for the change in gold and make it equal to the total change in iron, and then we're going to be able to solve for the final temperature of the two metals. So we're going to take the mass of the gold, which is 10 grams, times the specific heat of the gold, which was given, 0.129, times the change in temperature. Now here's the part that we don't know. We don't know what that final temperature is, but we are given the initial temperature of 18 degrees Celsius. And we're setting it up this way, and this is a question that's come up. We know that the higher temperature is the final temperature for the gold because the gold is going from lower temperature to warmer temperature. We're going to reverse that for the iron because the iron is going down in temperature, which means that we're going to take the mass of 20 times the specific heat given, 0.444, times the change in temperature. Now this time we're putting the initial temperature first. I know this is different from how we've done change in volume and things like that before, but this way it just keeps everything positive, right? Keeps the values positive by subtracting the smaller number from the bigger number. So whenever you're doing one of these types of problems, you're going to have one side where the final temperature comes first. That would be the one that's going from low to high. On the side of the substance that's cooling down, you're going to put the initial temperature first and the final temperature second. So we're going to work this out. A couple of steps here. We've got 1.29 times the change in temperature, 18 degrees, equals 8.88 times 55.6 minus the final temperature. We can simplify that a little bit by dividing both sides by 1.29, and we get final temperature minus 18 equals, I multiplied this through, I distributed, okay, and we end up with 382.5 minus 6.88 times final temperature. So that's 7.88 times the final temperature equals 400.5 degrees Celsius once we move everything around. And that means that the final temperature equals 50.8 degrees Celsius. Final temperature. This is a similar type of problem, okay, where we've got, in this case, we've got the metal and then the water is the other substance. We know the specific heat of the water. We know the temperature change on both sides. and we know the mass on both sides, what we're trying to find is the specific heat of the piece of aluminum. So we're using that same formula, change in energy, mass times specific heat times, times change in temperature, and the fact that we're assuming all heat lost by the metal is gained by the water to make the two sides equal to each other. So we know we have 8.6 grams of aluminum. We don't know the specific heat, that's what we're trying to find. And we know that the temperature goes from 100 down to 26.4. And then on the other side we've got 402.4 grams times 4.18 times the change in temperature of 26.4 minus 25. So that means 8.6 times C times change in temperature was 73.6 degrees on this side equals a total, if we multiply out the right hand side, of 2,354.84 joules, and then we divide, so we multiply 8.6 times 73.6, which is 632.96. We solve for C, and we get 3.72 joules per gram per degree Celsius. Okay, so a bomb calorimetry problem. The trick with the bomb calorimetry is you have to read carefully to see if it gives you the total heat capacity of the calorimeter or if it just gives you the capacity of the bomb itself, which is actually the metal container, and it gives you the amount of water. In this case, it's broken up. It's given the heat capacity of the bomb itself, the metal, and the amount of water. We know the heat capacity of water. So what we have to figure out is how much energy it took to raise the temperature of the entire calorimeter from 21.25 to 26.72. Once we know how much energy that was, we can work out sort of stoichiometry to figure out how many joules there'd be per mole of sulfur combusted, and then we can use that information to answer the question of the heat per mole of sulfur dioxide formed. So first we need to know what is the total energy absorbed by the calorimeter, which means the energy released by the reaction. So the energy of the water is 815 grams, that's an 8, times the specific heat of water, which is 4.18, times the temperature change, which is 26.72 minus 21.25. That comes out to 18,634.6 joules. Now for the bomb, which is the container, usually made of steel or iron or something, we've got the heat capacity of 923, and that's joules per Kelvin or joules per degree Celsius. Doesn't matter, they're the same unit, or sorry, same increments, so we can use the same number. Then we multiply that by the temperature change, which is the same amount, and we get 5,048.81 joules, which means the total amount of energy released by the reaction was 23,683.4 joules. Now, that was using 2.56 grams of sulfur. Sulfur is S8. which means that the molar mass is actually 256 grams. So we only burned 0.01 moles of sulfur. If we had burned 1 mole of sulfur, we would have gotten 100 times the energy, or 2,368,340 joules. That's burning 1 mole of sulfur. So if we set this up, we want to know how much energy is there per mole of SO2. Well, we know if we burn 1 mole of sulfur, we get 8 moles of SO2, which means that same number, 2,368,340 joules, is equivalent to producing 8 moles of sulfur dioxide. So that number divided by 8 comes out to 296,000 joules, or 296 kilojoules per mole of SO2. Okay, if we mix two aqueous solutions and the temperature of the water goes up by a couple of degrees, what is the enthalpy of reaction per mole of cesium hydroxide? Well, we know that we have a total of 150 grams of solution, because it's 100 of one and 50 of the other. And we're told that the heat capacity of the solution is 4.2 joules per gram per degree Celsius, very similar to that of water, which makes sense since it's mostly water. And the temperature change is 24.28 minus 22.5. We get an energy change of 1121.4 joules that was absorbed by the water, which means that's how much was released in the opposite direction. So the reaction released negative 1121.4 joules. That's the enthalpy of the reaction that we had, but the question is per mole. So if we have a 0.2 molar solution, we have 0.1 liters of that solution. That means if we have a solution that is 0.2 moles per 1 liter, then how many moles would we have in 0.1 liters, which is 100 milliliters? We would have 0.02 moles. So we have 0.02 moles, and that produced 1121.4 for 0.02 moles. So then how many joules would there be per 1 mole? And the answer is that there would be 56 kilojoules, or 56,000 joules per mole of cesium hydroxide. Okay, here's a couple of questions about this reaction. What would the enthalpy be if we multiplied the reaction by 2? Well, if you multiply the reaction by 2, you also multiply the enthalpy by 2. So in this case, it would be negative 2,905.6 kilojoules. If we reverse the reaction, you reverse the sign of the enthalpy change, so it would just go from negative to positive 1,452.8 kilojoules. And then the last tricky part here is, what if it was vapor instead of liquid water? So what if the water went from was a gas instead of a liquid? Well, in that case, you have to take into account that it takes more energy to produce water vapor than it does liquid water, because gas has higher energy. So we'd have to look up the standard enthalpy of formation of water vapor, which happens to be 40.65 kilojoules. And then, since there's 4 moles of water in the equation, we have to multiply that by 4. And we'd find out that it's 162.6 kilojoules. So the difference between the reaction that we have and the reaction if this was water vapor instead of liquid water is that there would be a difference of 162.6 kilojoules less coming out of the reaction, because that energy is now going into vaporizing the water. So we're going to subtract that from our 1452.8 kilojoules, and we would see that the reaction in that case would be 1290.2 kilojoules. Okay, so the amount released is lower because some of the original energy is now being used to vaporize that water, and therefore the amount that you get, the net result, is somewhat smaller. Okay, here we go. Heats of formation to calculate the enthalpy change for the following reactions. A couple things you have to keep in mind here. You're going to have to look up the heats of formations if you're doing these problems on your own. If you get them on the test, you'll be given the information you need there. Be very careful with a couple of things. Make sure you pay attention to the state of the substance, because, as we just saw in the last problem, the difference between the heat of formation of liquid water and the heat of formation of gas water, water vapor, is different. Same here, hydrochloric acid gas in the first one, or hydrogen chloride gas in the first one, is different from aqueous hydrochloric acid, or even solid, in this case solid sodium hydroxide is different from aqueous sodium hydroxide. So you've got to make sure you're looking at the chart, you look at the right substance. The other thing that you have to remember here is that the heat of reaction, standard heat of reaction, is equal to the sum, that's a sigma, believe it or not, of the heat of formation of the products minus the sum of the heat of formation of the reactants. So you have to look at both sides, take the total amount of the product heat of formation, add it all together, subtract out the heat of formation of the reactants, because you're not forming the reactants, you're actually breaking them apart, so you're reversing that reaction. And then whatever's left over is the final heat of reaction. So for the first one, for A, hydrogen chloride gas has a heat of formation of 92.3. Hydrogen ions, aqueous, have a heat of formation of 0. There's a few, typically things to look out for is elements like O2, Cl2, N2 have heats of formations of 0. And there's a handful of other things like the hydrogen ion that have 0 heat of formation. And then the formation of the chloride ion is negative 167.2. Okay, so then the heat of reaction is equal to the sum of the products, which in this case is just negative 167.2, minus the heat of formation of the reactants, which is 92.3. So we're really adding 92.3, so the standard, that's what the little circle means, by the way, standard heat of formation of the reaction is negative 74.9 kilojoules. Next one. For the sodium hydroxide, 2NaOH plus CO2, and then Na2CO3 plus H2O. And again, here's where you have to look out. That's gas, so the heat of formation is different for the gas than it would be for the liquid. So the heat of formation of sodium hydroxide solid is negative 425.93. Since there's 2, we'd have to double that. CO2 gas has a heat of formation of negative 393.509. Sodium carbonate solid is negative 1130.77. And water vapor is negative 241.818. So, the heat of the reaction is, add up the products, we get negative 1372.59, subtract the heat of the reactants, which is a total of negative 1245.37, and we get final answer, heat of reaction, equal to negative 127.22 kilojoules. Next one, C2H2 combines with H2 to form C2H4. Everything here is in the gas state. Hydrogen gas, elemental gas, 0 heat of formation. C2H2 226.73, and heat of formation of the product is 52.3. So the overall heat of the reaction is equal to the products, 52.3, in this case there's just one product, minus 226.73 plus 0, which means that the heat of reaction is negative 174.43 kilojoules. Okay, and the last one, NO2 and 2O4. Well, this isn't a balanced equation. This has got to be a 2. So when you look up the heat of formation, it's plus 33.2, but we've got to add that twice, 33.2. And then the heat on this side is 9.16. So the heat of the reaction is equal to positive 9.16, minus 66.4, which means that the heat of reaction is equal to negative 58 kilojoules, rounding. Okay, so this time we're given the equation and we're given the heat of the reaction. We need to find the heat of formation of one of the substances in the reaction. So our X is the heat of formation of N2H4. O2 is an element, no heat of formation. N2 is an element, no heat of formation, and we're told, or we would look up that the heat of formation of water vapor, we've used this one before, 241.88, and there's two of them, 88. So that means that the heat of the reaction, which is negative 534 kilojoules, is equal to negative 241, not negative 241, it's negative 486 43.616 plus 0 minus X plus 0. Okay, so we do that out and we get negative 50.384 is equal to negative x. Therefore, the heat of formation of the N2H4 equals 50.384 kilojoules. Okay, given the following data, calculate the enthalpy of the reaction. So you have to look at where are the substances and where do you want them. So the key one to change here, because you only need to change one of them, is that we need to reverse the first reaction. So I'm going to reverse that reaction and it becomes H2O produces H2 plus 1/2 O2. And since I changed the direction of the reaction, I have to reverse the sign of the reaction, and it goes from being negative 285 to positive 285 kilojoules. And the other two are going to stay the same. So really all I'm doing is I'm going to take that one out because I've reversed it down here. Now I can add these together. I can cancel out half an oxygen on either side. And then I can add together, I can also cancel out the calcium monoxide. And that leaves me with Ca plus 2H2O yields CaOH2 plus H2. And then if I add all those enthalpies together, I get negative 414 kilojoules. Okay, now this last one is a bit tricky because it looks like nothing's going to work out because the numbers, you've got more of certain things than you want, and other things are like 3 on one side and 2 on the other. So the first thing, like with everything else, the first thing to do is look at where you need to reverse a reaction. And in this case, I'm going to reverse reaction A, and I'm going to reverse reaction C. I'm going to leave reaction B alone in terms of the direction. So what I end up with for A is 2Fe3O4 plus CO2 yields 3Fe2O3 plus CO. And then I reverse the sign and I get delta H equals 47 kilojoules. I'm going to leave B alone. I'm going to reverse C, and it becomes 3FeO plus CO2 produces Fe3O4 plus CO, and the enthalpy goes to negative 19 kilojoules. Now here's the really tricky part. And what you kind of have to do here is just look at what you actually need, multiply by the simplest possible numbers, or do the simplest possible thing, and then most of the time, if you do that, things are going to work out. Okay, and don't panic about, oh, I've got different numbers and different fractions and things, because there's a lot of different substances here with different numbers in front of them. And we're just going to go through here. We're going to use the numbers that we have to multiply each reaction, and they will all cancel out in the end to give us what we want. So first thing I'm going to look at, reaction A. I need to get this down to a smaller amount because the numbers just don't work out here. I'm going to multiply this entire thing by 1/6. I'm going to multiply equation 3 because I know I only need one FeO. I'm going to multiply equation C by 1/3 to get that FeO down to 1. And then I'm going to go back up to reaction B, and I'm going to multiply it by 1/2. Okay, because I only need one Fe on this side. So I'm gonna rewrite these equations after with the multiplication in here and everything in the order that I wanted it, and then you'll see how everything cancels out. So taking equation A and multiplying it multiplying equation A by 1/6 leaves me with 1/3 Fe2O3 plus 1/6 CO2. Now remember, I reversed this reaction, so it looks different from what's up here because I reversed it and then I multiplied it. And then on the other side, I'm going to have 1/2 Fe2O3 plus 1/6 CO. And then the enthalpy, because I multiplied it by 1/6 after I reversed it, becomes 7.83 kilojoules. That was A. B, I multiplied by 1/2. So I have 1/2 Fe2O3 plus 3/2 CO produces 1 Fe plus 3/2 CO2, and the enthalpy, because I multiplied by 1/2, is negative 12.5 kilojoules. And then reaction C, I multiplied by 1/3, so I have FeO plus 1/3 CO2 yields 1/3 Fe2O4 plus 1/3 CO, and the enthalpy is negative 6.33 kilojoules. Okay, now you got to add all that together. Okay, again, it's not immediately obvious maybe, but we have 1/2 Fe2O3, 1/2 Fe2O3. We have 1/3 and we have 1/6. So if we do this in 6, this would be 2/6 plus 1/6, which is 3/6 or 1/2, which cancels out 1/2 of my 3/2 CO, leaving me with 1 CO, which is what I want down here. 1 CO is going to carry down. The same thing with the CO2s. I've got 1/3 and I've got 1/6, which is 3/6, and I've got 3/2 on this side, so I'm canceling 1/2, which leaves me with 2/2 or 1 CO2, which I want. And then I've got 1/3 this should have been Fe3O4. That's what's going wrong here. 1/3 Fe3O4, 1/3 Fe3O4, which leaves me on this side with FeO plus CO yields Fe plus CO2, and it leaves me with an enthalpy change of negative 11 kilojoules.